Physics Bites.
Physics Bites,
A science podcast in English by the students of Notre-Dame d'Association.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre-Dame d'Association here in Paris. We are continuing with our senior classes presentations. Last week you guys listened to an interesting topic around the interpretations of quantum mechanics, and this week we're kind of doing a follow-up on that and sort of taking up what some of the work on those interpretations did for the advent of quantum computing. So I have two new senior level students here who are going to be talking to us about quantum computing. I'm going to let themselves introduce themselves.
Hi, I'm Colombe. I'm in terminal at Notre-Dame d'Association, Okay.
And you are?
Hi, my name is Emma, and I'm also a senior at Notre-Dame d'Association.
And you guys were both also in the class last year. What topic were you guys working on last year?
Nuclear energy.
Right, and you were?
Nuclear energy.
I guess we're in the same.
Yes.
Yeah. Okay. And I have a co-host today that you might have heard last time.
So, hi, my name is Gabriel, and I'm also in terminal with.
Right. So Gabriel was one of the duo that last week talked about the current interpretation of quantum mechanics. So he's here as a co-host to ask a few questions and help his classmates on the topic of quantum computing. So let's get right into it. I'm going to ask you guys right away, what is quantum computing? How about we give a general overview of it before we go into the details of how we go about doing all these things and the rest?
So basically it's a way, it has to do with quantum physics that Gabriel taught last week, because it uses the principles of quantum physics, but in computing. So there are a few differences between classical computers and quantum computers, and they work thanks to quantum physics, and that's basically what quantum computing is.
So basically we're doing computers, but we're kind of going to take advantage of some stuff that are exclusive to the domain of quantum mechanics, and this is supposed to make the whole thing better, different. I guess we'll get into details of it. So why don't we start with maybe a bit of a timeline, a bit of history of quantum computing. You guys mentioned a few major names that come up in the history of this. So why don't we start with that?
To give a little history about quantum computing, first in the 1980s, Richard Feynman suggested that classical computers were not capable of accurately simulating quantum systems, and so that started the research for quantum computing. Then one of the most important figures of quantum computing is David Deutsch, who formalized the concept of a universal quantum computer in 1985. And following this discovery, in the 1990s, there were major breakthroughs in this field, and to this day, in the 2010s, research moved from theory to experimentation, and
right, that's when we actually start building quantum computers, the different types, and it's still continuing, and it's sort of gone more from the university and purely academic setting to Google's making their own quantum computer and Microsoft is doing their own, so because it does require a lot of money.
On the market now, it's important.
Right, and we actually have commercialization of certain sort of limited capacities of this. Okay, so I think we can move on to the heart of the matter, like what the key concepts of quantum computing are. Just to put it into contrast, the basics that we need to sort of know, I think, about classical computing is that the way computers work is that they store information in what we call bits. So these bits materially are what we call transistors, and these transistors can be in one of two positions, which corresponds to 2 bits of information, whether they let the current pass or no, the zeros and the famous zeros and ones in binary information, and then we sort of string these along together, and the more of them we have, the more information we can have, and that's kind of it. Which is why binary numbering is what corresponds to the sort of mathematical side of information theory, which materially goes to these transistors. And that's something that's fundamentally different with quantum computers, if I understand this correctly. So maybe we can go into what is the fundamental differences, why it's better, is it better, if so, why, and all the rest. So I'll let you guys maybe get started on that.
Quantum computers, instead of using bits, they're using what we call qubits. So we have...
which is short for quantum bits.
Yeah.
Right.
So that's like tiny physical systems. And instead of being either in a state of 1 or 0, they can be in a mixed state.
Mm-hmm.
So those qubits, what is fundamentally different from classical bits is that we use principles of quantum physics, and we apply them to the bits.
Okay.
And
so what are those qubits, physically speaking? So in the case of a classical computer, the bit is stored in those transistors, which is just like a tiny switch. And what we've managed to do for the last 50, 60, 70 years is to make these transistors smaller and smaller. And that's why we have more and more of them in our little microchips, and that's how we've increased our computing power. What is the equivalent of a bit, physically speaking, when it comes to quantum computers?
They're like tiny particles, which can be atoms, maybe photons.
Okay. Well, I think photons are maybe more difficult to manipulate, so the ones that we use are basically atoms, right? So the advantage of that being that they're pretty small, right? So we can have more of them. Okay. What else? What else can we say about these qubits and the way they help a quantum computer work?
Just to say how they are... Emma said they were photons, things like that, but how they are created generally is by manipulating and measuring systems that exhibit quantum behavior. So such as photons, electrons, and traptions and atoms. But there's different forms of qubits. So
Okay. And how do we use these qubits? How do we use these trapped atoms or ions or whatever else is playing the role of a qubit? How do we do computations with it?
Thanks to quantum principles, but like entanglement
So Emma, I think you're going to go more into technical, physical details of this, so go ahead.
So the first principle is superposition, so that's what gives the qubit the ability to be either to be in a mixed state of 0 and 1.
So in comparison to a classical computer, what is the difference here?
A classical bit is either 1 or 0.
Okay.
It cannot be in a in-between state.
Right, in a superposition. And superposition was one of the fundamental properties that you guys talked about, Gabrielle, last week when you talked about interpretation of quantum mechanics, right? Okay. So this is one fundamental difference. In a quantum computer, we can have mixed states of our qubits, whereas in a classical computer, it's one or the other. How is this making a difference?
Well, for every applications that we'll be doing, for example, simulations, it can be a great help. Because, for example, if I'm simulating thousands of situations, well, a classical computer will have to go through every one of them, like one by one.
Right.
So that takes a tremendous amount of time. Whereas a quantum computer, well, this superposition state of qubits will help us kind of simulate every possibility at the same time.
Right.
So we reduce the amount of time by a great
amount. So in a way, a classical computer can only do operations in series, whereas because of this fundamentally quantum property, which is superposition, a quantum computer can do calculations in parallel. So that should, depending on the type of operation we're doing, this could reduce time like tremendously. Okay. So for example, in our phones, in our computers, our chips that do all the calculations, they have billions of transistors, right? And each of these transistors represents one bit often. Is it the same then in a quantum computer?
No. Because of the superposition principle that we're using in a quantum computer, well, if I have a series of 2 bits, classical bits in a classical computer, I'll only have few outcomes of those 2 qubits. Those 2 bits. But if I use 2 qubits, I'll be able to represent way more.
Right. I guess states and combinations of states.
And if I add more and more qubits, well, the number of outcomes will be exponentially greater than a classical computer.
So ideally, we can sort of think that a really, really powerful home computer that you have, which has billions of transistors doing all the calculations, in a quantum computer of equivalent power, you would need maybe a few hundred or maybe a few thousand of these qubits or atoms. Would it do exactly the same thing, or is it doing different things? Can we use a quantum computer completely to just replace a classical computer, or are they good for some things and not so good for other things?
Well, we could replace them. Like that's not something we could not do. But the purpose of the quantum computer is not the same as a classical computer. So we'll be able to do other types of calculations and like I don't know. Well, I think I'll be talking about it.
Right, because you talked about also a lot of stuff like Shor's algorithm, Grover's algorithm, and all these things.
Basically, just the quantum computer is able to do other things better than the classical computer.
Okay. Gabriel, if you have any questions at any point, you can feel free to jump right in, no? Otherwise, I was thinking about maybe, so the way you make it sound, these things look miraculous, right? This seems like the perfect thing. How come we haven't made any quantum computers really to the state?
Basically, it's because of the fragility of qubits, because they depend a lot on the outside, if you get the idea, the noise and the temperature. And so we have to, quantum computers have to be built in a very specific settings and
in conditions that are very difficult to maintain.
And so it's really difficult. And also there's a problem with errors. There's a much higher state of error with qubits.
And one of the more it's become interesting and more important fields in quantum computer in the physics side is what we call quantum error correction, which is very complex. I have no idea what it is. I just know that it's very important, and that a lot of people have gone into it and found it super interesting because it's actually very, very, very physicsy and very quantum physicsy. Gabriel, I think you had a question.
Yes, was about so the error, was it because quantum system makes so much errors? Is it because of this we won't use them like for our usual
to play video games?
Yes.
Yeah, but that's also because if, like Emma said, if we want to build quantum computers, it's for other purposes that will, like, it makes more sense to use them for this than for simple tasks that can be done by just classical computers.
So the idea is that they're not supposed to just replace classical computers, but they're better at some tasks that classical computers would take a long time to do.
It's like they could replace them, but that's not the point.
That's not the point. That's very well said. Okay.
For the energy that is needed by a quantum computer, I think it's really high. So is there any big needs? Like, do you know how much electricity it needs?
How much energy?
Yes,
like the current quantum computers that we have actually built.
I think it's still
it's a big supercalculator. So is it need less or more?
Like less or more energy as a classical computer?
Like if you take a big supercalculator, do you think it's more efficient to? Because I think
that's a very difficult question to answer, just because we don't have a lot of. There are no commercial quantum computers.
Yeah, I think
there are very few in the world, and I think they're pretty.
It's like supercalculators needs to be cooled down, and it is also for.
But it's also something with quantum computers because of the temperature and.
I get the impression that the question is not the amount of power to do all those operations, but it's the fragility, I guess, of the configuration. Is there? Because you guys also mentioned, for example, the question of entanglement, which is a fundamental property in quantum mechanics that your classmates brought up last time. We also talked about, for example, the interactions between atoms and quantum system with the exterior. Can you just talk a little bit about what we mean by noise? What is the origin of all this high fragility of these systems? Why is it that they can be very easily sort of perturbed and messed up, and why there's so much complexity required to keep them?
I think it's because about the state of qubits and the fact that superposition and everything, it's much more. I think that's what makes them much more fragile, because they are irreversible. I don't know how to say this, but
well, because the superposition state only kind of works until you measure the state of the qubit, and measuring is like knowing if it's a 0 or a 1, 0.
And concretely speaking, measuring is the word we use for any kind of an interaction, right? Even if it's an involuntary interaction, even if it's like a stray atom coming in from the air and sort of getting into contact. So it's so easy, I think, Gabriel, you could probably talk about it a little bit given that you did the topic on quantum mechanics, but there's very high difficulty involved in isolating a system of atoms and keeping it in a specific state without having any interaction from the outside, which is why temperature, like you mentioned, is also important, because temperature, the higher the temperature, the more, I guess, the outside atmosphere and the system are going to be in movement, and there's more chance of, I think, like interaction and sort of messing up the system. Right, and this was what you talked about when you talked about the architecture of these quantum computers in your presentation. Okay. Maybe we can move on to not the actual physical construction, but let's talk about, I think Emma, you brought it up, how they operate, how there are applications and algorithms that can be used with this. So let's go more to the, I guess if we can use the word, the software side rather than just the hardware.
So right now, what we're doing to use all those qubits together is using algorithms. So we have two algorithms that are very important for this field. So first of all, the Shor's algorithm, which is the integer factorization algorithm. Right,
and this was discovered in which time period?
I think it's 1994.
Yeah, I think so. This was David Shor, who's an English mathematician, who came up with it. What is this algorithm supposed to do, and why is this so seminal and so important?
Well, it can factorize really big integers, like integers with maybe 1,000 digits. And factorizing those integers will help us decode encrypted data. So, for example, right now what we're using is RSA encryption. So that works with a public key and a private key. So basically speaking, when you send an encrypted data, with those two keys, the receiver can
open the message, decode
the message. And so there's one key, the private key, which is only known by the receiver, and it has to do with integers and arithmetic.
Like a 256 number, I think, 256 character number, which is supposed to be so high that classical computers cannot factorize it easily or within a reasonable time, I think.
In 2020, we had 250 digits that were factorized, but that's kind of the biggest integer that we could factorize, because otherwise it's way too, it takes up a lot of energy and time.
Okay. So what makes Shor's algorithm so important then?
Because when you use Shor's algorithm, it will simulate every possibility to factorize an integer, which is, again, the principle of RSA encryption. And so if you can use a Shor's algorithm and a quantum computer to factorize integers, they'll be able to decrypt kind of every single message.
Right, which means that with a quantum computer and this algorithm, we lose all encryption, which is potentially catastrophic given how much very important information we have, whether it's military, health related, social, political.
Right now it works because you need a lot of time and like it's very time consuming, and the more digits, the more time it takes up.
Right.
So because quantum computers can simulate every single possibility in a very short scale of time, we'll be able to decrypt a lot of data really fast. So RSA encryption will be kind of useless.
Right, it becomes completely defunct. You also talked about Grover's algorithm. What is that, and what is it, the importance there?
It's known as the searcher's algorithm.
Okay.
So in a data list, which is unorganized and unstructured, you can find the data you want, and like in a very little short scale of time.
Okay.
And so
and the specificity of these algorithms is that they're conceived to be used with a quantum system, not with a classical one, right?
Because it harnessed all the quantum physics
properties. Yeah. Okay. Have there been, to your knowledge, any other major breakthroughs in terms of these sorts of algorithms in the meantime, or I'm sure there have been other ones. These are just the two major ones in terms of like breakthrough moments. Okay. Maybe we can sort of move on to more future prospects of quantum computing, right? So for as long as I remember, when I was your age, we were talking about quantum computers and optical computers and all these things, and we're like, oh, it's going to be a revolution. And then time passes, and we still hear about them, but it feels like the future is always 20, 30 years away. Maybe we can go into maybe looking at where the future lies as of today and what you guys found in your research. So, Colombe, do you want to maybe get us started on that?
There have been a few breakthroughs, if we can say that, basically about qubits, because the biggest problem about quantum computers is that the fragility of qubits, and so nowadays there are a lot of research about qubits, and we found some types of qubits that are being used to continue in this field. So, for example, Microsoft developed topological qubits.
Okay.
So qubits using topological materials. So I don't know if I can explain what a topological material is.
Maybe in a very general way.
It's just materials where electricity flows easily on the surface and or the edges, but not on the inside. Through the inside. So this materials makes the qubits. So the objects can't are them real easily. So I don't know how to explain. They are more resistant.
Okay.
Thanks to this material.
So it increases the stability of the system.
And so the noise is less disturbing for the qubits. Okay.
And this is sort of in a prototype state, or is it being worked on?
It's been worked on by Microsoft. It's a project called Majora 1, I think. Majora 1, yes. And so that's one type of qubits that's being developed.
Okay.
And there's also logical qubits.
Okay, logical qubits.
It's about the error rate. Another problem. So they are error-corrected qubits, I think. And so they are more theoretical than the others, because they are still a lot of research about them, but it can lead to less error and.
Which is one of the big problems, right? This is one of the big things that has to be dealt with. Is this question of quantum error that comes from noise. You guys also mentioned at one point quantum dots. What are quantum dots? I don't think I understood clearly. It was part of the current technologies that you guys were talking about. You talked about superconducting qubits and trapped ion qubits, and then you talked about quantum dots.
Yes. So they are small semiconductors.
Yeah.
And they. Okay, I have to say it simply.
The simpler the better.
Yeah. They can capture a single electron.
Mm-hmm.
And they use this electron as a qubit. That's not the interesting part, but and so that offers promising potential for scalability, and because they can, I don't know, using this electron as a qubit, it offers more stability and.
Okay, I guess the name of the game always is stability. How to be more stable and less fragile. Okay, I understand. It's a very complex field, and I think it's very difficult to talk about it. Not being able to actually do any of the physics, so it's not that easy. Do you guys know what quantum supremacy is? I think you mentioned it at one point.
Quantum supremacy.
Yeah, it's a term that we hear a lot in sort of like science news around these things. And
yes, it's showing that it is possible to solve a problem in just a few hours, while a classical computer would need a lot of time.
Okay, so it's the idea of the threshold where quantum computers become advantageous to class. Have we reached quantum supremacy? Is that something we're going for? Have we reached it in some cases, but in not other cases?
Well, I think it would be great to kind of reach this quantum supremacy, because at that point we could actually start to commercialize those.
Okay.
And maybe like big companies and everything could actually need it.
Okay, so maybe on that point, do we use quantum computers currently for anything, or is it just all research machines and just still very academic work?
But it's still a lot of research, but there are big firms that are beginning to put quantum computing on the market
and have actual applications for them. What are some applications that we have or we will have once quantum computers are a bit more prevalent?
But basically for cryptography, yes.
Everything about cybersecurity, because we really use a lot of RSA encryption, even in bitcoins. Like, we could actually, with the use of a quantum computer, be able to take bitcoins from people.
Because, how so?
Well, in the same way we could decrypt maybe
like any sort of information that's being sent,
Well, bitcoins also use a private and a public key.
Right.
And so maybe you could access to an account of or something like that.
Okay. So any place which is under sort of high degree encryption risks being exposed, right? But speaking of Bitcoin, maybe also quantum computers can be used to actually mine Bitcoins more rapidly or more efficiently than classical computers, I suppose. That's
And do you know if they could be used in AI topics? Because like you talked more about algorithms that are linked to arithmetic, and I know that AI is more like matrix reduction and it's not the same field. So do you know if you could possibly use them?
I think we're kind of investigating around the convergence of AI and quantum computers, like what it could give, because we have advantageous sort of skills in both parties. So, for example, AI could quantum computing could kind of predict a lot more accurately.
Okay.
And I don't know, maybe AI could kind of give more ideas or something like that.
Okay, it's very speculative. I think it depends on what kind of AI, right? Like, obviously, I don't think using quantum computing for like LLMs, the way we have the large language models, like anything that is produced by Claude, ChatGPT, all these things, would not necessarily be neither a good use of that nor particularly advantageous. But I guess depending on other kinds of AI, for example, off the top of my head, I would think it's something like any AI which is supposed to play games which are very complex and yet simple, like Go, or like problems like biophysical problems like protein folding and stuff like this, which require very, very, very heavy calculations. I guess if that is something that we can develop an algorithm for, maybe it's much more advantageous. Or protein formation, drug formation,
they are actually kind of searching the use of quantum computers in the drug development field. So because a quantum computer could actually simulate every kind of interactions of molecules and drug development. And so maybe that could actually decrease the number of failed trials. So for example, for diseases that we don't actually and currently have a medicine for.
Okay. So there are actual applications that we're starting to come up with and maybe apply this to. And I think as a physicist, I think we can always come back to the idea there's a lot of physics calculations, a lot of quantum calculations which are very difficult that we can't do well enough with, or at least quick enough with classical computers, that a quantum system would be really good for that, right? Something like we've had recently stuff around of calculations around wormholes, like micro wormholes, and like other things like that. Okay, well, I think we've gone as far as we can, given that the topic is very, very advanced, and you guys are only in high school for now. It would be, if you ever end up doing any quantum computing later on, maybe we come back and do an update on the podcast. Maybe we can finish up on maybe getting your thoughts on how you found the topic, because I think on top of everything else, Colombe, you're not even doing physics this year.
Yeah, but I think actually that's what I liked about this subject, because it's really challenging. Like, quantum physics is really hard, and quantum computing, I think, even more, because it's more specific.
Very technically advanced in terms of applications.
Even classical computing is hard for me.
But that's true, because we never actually study how computers really work in school, right?
So I like the fact that it was challenging, and I learned a lot of things, and I think it was really interesting. Yeah.
Okay, Emma, you are doing math and physics this year, so you're more scientifically, I guess, prepared. But I imagine it was still a pretty tough topic.
Yeah, it was kind of tough. But what's kind of cool was that a lot of kind of principles were based off on what we're actually studying this year.
In math, especially, I guess.
Yes. Yeah. With all the arithmetic.
Right, all the factorization, arithmetical calculation theorems.
Quantum interference. So that's also kind of based off on interference.
Just like wave mechanics that we've seen a little bit of. Okay. So it was a challenge, but not so much that you were overcome by it. And you guys did a pretty good, frankly, presentation on a really tough topic. I was a bit reticent when I gave it to you guys, but you guys did a great job and overcame the difficulty of the topic. Okay, so Gabriel, do you have any final thoughts, questions, comments for your classmates?
Well, it was interesting. I don't have any questions left, because I think that we've gone on all the subject.
Right.
And
you did a pretty good job. Great. So, thank you very much, Colombe and Emma, and thank you, Gabriel, as a co-host. I hope our listeners enjoyed as much as I did. Thank you.
Thank you.
So, that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.